Okay, welcome to lecture. We have an exam on Thursday, our first midterm. Before we get into exam one procedures down here in Roman numeral 4, I'd like to go over a couple things in web courses and then the rest of lecture. First of all, you're going to have a little study assignment in web courses. It's actually been in there since I think Saturday, and it will activate today after class. It's really meant to encourage you to dive into the extra readings on the extra readings page, and so look at those extra readings and then try to tackle. I think there's like four questions, so it's not grievously ginormous, but you do have to read the extra readings to tackle it. Also, I highly encourage you to study everything in masteringastronomy.com. In other words, all the homework that we've done. Just review that, and that'll be helpful. I want you to study everything, of course, but don't forget to study the homework in masteringastronomy.com because a lot of it's actually kind of a tutorial type homework. And then do this mini assignment in web courses. Another announcement about web courses, there's a link there for the UCF Astronomy Society. And one of the nice things that they do is they sponsor public viewing sessions on Wednesdays and Thursday nights, depending on their schedule and depending on the weather. And I was looking at their website a couple Thursdays ago, January 28th. They wanted to go, but they couldn't. And so that row here in their schedule table is red. Last Wednesday they did go, and I regret that I didn't encourage you guys to go. It was a beautiful night. This Thursday night, hopefully, it'll be nice. I just looked at it before coming down to the lecture hall. Thursday is now marked yellow, so they haven't decided yet. It's still a maybe. Keep an eye on this page. There's a link to it inside web courses under UCF Astronomy Society. And the deal for us is if you go, they have a handout that UCF students can fill out and turn in to them, and then they turn it in to me, and I give you guys bonus points for that. And I've been trying to figure out what to do for. Let me go ahead and use this one. I've been trying to use or trying to figure out how many points for attending and participating in the observing sessions. And everybody can go to it. I mean, hopefully everybody, if you live fairly close to UCF. And so I think I'll do is give you 10 bonus points for attending and doing the observations, filling out your handout, and then turning it into the astronomy guys. And you can go as many times as you want, as many Wednesdays as they have sessions, but we have no guarantee of any sessions in the future. The weather can just change like that. But if you can make it more than once, if you can make it once, good. If you can make it more than once, even better. And I highly encourage you to go multiple times because they'll have different things to look at every time. So you might look at Jupiter one night and then check out some constellation or a group of stars in the Big Dipper or something like that the next. And all of it will be helpful for us in our lectures. Okay, I was just talking about homework in masteringastronomy.com. Our very first one over there, regular homework assignment, was on spectra. And I want to go over a couple things about spectra just to fill in a few gaps that I didn't get to earlier in the semester. Now we know that the spectra of elements are like their fingerprints, and either the emission lines or the absorption lines. And I want to emphasize that the absorption lines or the absorption features, the emission lines or emission features, those are relative to the continuous spectrum of a thermal source. So in other words, when you look at a thermal source and you see absorption lines like this, these are absorption features. This is what your eye would see up here. All right, if you were looking through a diffraction grating like we did in lecture, you'd see gaps in it. If you were using a photometer, some kind of a device to measure the level of light, it would look like this. You'd have kind of a curve of continuous intensity increasing to a maximum right about here, but then a bunch of bullet holes drilled into it. And those bullet holes for the photometer or the gaps for the naked eye observation, those are the absorption features. The photons are not coming through, so there's a dip in the brightness. And what I want to emphasize to you today is what the ideal spectrum looks like. We've seen these absorption lines and emission lines. We saw emission lines in lecture. And I want to show you what an ideal spectrum is. In other words, this continuous curve, if it didn't have any bullet holes, it would just be kind of a graceful curve, increasing in intensity and then decreasing on the far side over by the 700 nanometer range. And so I want to go through the idealized spectra with you. So let's take a look at what the ideal spectrum looks like. And you better take some careful notes because I'm going to ask you questions about this on exam 1. That's why you're getting this extra little instruction. The thermal source, the thing that we looked at, the incandescent light bulb, has a very particular distribution of energy by wavelength. And it was very difficult to understand about 115 years ago. And it came under the theory came under the name of blackbody theory. In other words, think of an object that is a perfect radiator of energy as well as a perfect absorber of energy. And so because it's a perfect absorber, it absorbs everything. It is called a black body. Now, that's not the same as a black hole, but it is called a black body. And nobody could figure it out. I mean, they approximated a black body, an ideal radiator, an ideal absorber in various ways. For instance, drilling a little hole into a burning fiery furnace and then measuring the intensity at all the different wavelengths that come streaming out through that little hole in the burning fiery furnace. And they couldn't figure it out. This is what they found. They found that at short wavelengths, there was relatively low level of intensity or radiance, and that the peak wavelength came up, or at a certain wavelength, there was a maximum amount of radiance, and then as you went to longer and longer wavelengths, the radiance would go down again. Now, nobody was able to figure that out until Max Planck in about 1899. Very famous guy. And his theory was basically this, that if the energy is emitted in little bundles of energy, the size of the bundle depending on the frequency of the light, then everything fits. This entire curve is comprehensible. But if you insist on energy being emitted continuously like a wave, going across the sea, or a wave washing up on the beach, just continuous wave upon wave upon wave, you can't figure out light. You can't figure out the distribution of energy from this idealized black body. Any thermal source is not comprehensible in that way. But in the quantum hypothesis, Where energy comes out in bundles, yes it is. And Max Planck is the one that developed the physical explanation for why the radiance of a black body has this particular shape. You know, kind of a bump and low intensity in short wavelengths and low intensity on higher wavelengths. And at the middle wavelength, higher intensity. And he also found out, or he conjectured, that it went by temperature. And we're going to look at that carefully. This is the actual idealized black body spectrum for something that has the same temperature as our sun. The temperature of our sun is 5,800 on the Kelvin scale, the absolute Kelvin scale, which you can read about in the textbook. I believe I talked about it a little bit already this semester. 5,800, that's the surface temperature of our star. Now, we have looked at the spectrum of the sun. It produces a rainbow of light, all the colors, Roy G. Biv. It produces ultraviolet, it produces infrared, but there are gaps in it, remember? Remember we saw those bullet holes, those gaps in the spectrum? So this is an idealized, this is what the sun would look like if it didn't have any absorption features, all right? You would have a lot of energy at this wavelength and not so much down here at these shorter wavelengths, and then again, not so much down here at longer wavelengths. Now, if you want to look at this, here's your study note, page 116 and 117. And I believe it's chapter 5, the cosmic light, the cosmic messenger. But for sure, it's page 116 and 117. Now, let's take a close-up look at this black body spectrum for our star. Okay, here's the close-up. And down here across the bottom are the wavelengths, and the vertical scale is what we call the radiance, or the intensity of the weight at each wavelength. So at 4,000 nanometers, or excuse me, at 4,000 angstrom units, you have an intensity right up about here, fairly high up. But then down here at 10,000 angstrom units, the intensity is right about here, and so that's a little bit lower. Now, what is an angstrom unit? Recall that 10 angstrom units is the same as 1 nanometer. So go ahead and write this down. 4,000 nanometers is, 4,000 angstrom units is the same as 400 nanometers. Now, 400 nanometers is important for us. Why is 400 nanometers important? Raise your hand if you know the answer to that. That is correct. 400 is the shortest wavelength that we can see. So that's red light, correct?
I think it's purple.
It is. It's violet. It's not red, it's violet. 7,000, right about here. This is the red side of the visible. Okay, so try to draw a graph and going out 2,000, 4,000, 6,000, all the way out to 16,000, and then try to draw a curve as well as you can that peaks at about, 5,000 or so. All right, here's the peak. And here's 4,000. Here's violet. All right. And what I've done to help you is put these little bars here to indicate the relative intensity of the red wavelengths, a small bunch of red wavelengths, and a small bunch of violet wavelengths over here. Now the peak wavelength is right here in the middle. And for the sun, that's actually a green, kind of a yellowish green, which is what the color I chose for this bar. So these three bars indicate the relative intensities of the three different colors in the visible part of the spectrum, in the Roy G. Biv part of the spectrum. Okay, 400 nanometers, 4,000 angstroms, that's violet. That's this bar right here. Okay, and the biggest bar is green. That's right here at about 5,000. And then 7,000 we have red, and what I want you to remember about this is that the relative distribution of energy is important, and it's almost like a signature of the temperature. In other words, in our star, green is the brightest. That's the biggest bar here. That's where it peaks. That's where its theoretical blackbody spectrum peaks. And in real life, the sun, it's a big thermal system with absorption features, but this is where the peak of the sun's spectrum is. It's pretty well measured. But then the second of the three bands that I've represented here, the second biggest is violet over here, and then the weakest is the red. Now, another star might have a different temperature, and so it'll have a different combination of colors. Okay, and one of the ways that we can use that different intensity ratios is something called the color index. And we'll probably talk about that in 2 weeks, a couple weeks, the color index. But yep, it's coming up. And the color index is a way for us to measure the colors coming from a star and see which one's most intense, which one's least intense, and then assign a temperature to it based on those colors. Now, I'm going to show you a blackbody spectrum for another star that's fairly close to us. And it is a star that I've mentioned before in class, one that you can see every night that's clear anyways, and that is Sirius, Sirius A. So here's the next blackbody spectrum. And here's Sirius A, this black curve. And here are the color bars for our star, the sun. All right, so they are way out of whack. That's what the sun's set of color bars were. But for Sirius, the color bars are way different. So let me diminish these color bars to the right levels. Okay, first of all, red, it's down here. Green, that's dipped down. Now, violet here is actually a little bit bigger. Watch this carefully. I have to raise the level of violet. Here it comes. It's actually a little bit taller. So the violet output of Sirius, in terms of the visible wavelengths, is just a little bit brighter than the violet output of the sun proportionally. And the green is quite a bit smaller, and red is smallest. So for our star, the green was the most intense, but not for Sirius. Sirius, of the visible colors, violet is even more intense. Now look where the peak is. Whoa! The peak is down here about 3,000 angstrom units. That's 300 nanometers. Infrared or ultraviolet? 3,000 angstrom units. Ultraviolet or infrared? Raise your hand. Raise your hand if you have an answer. Who's got an answer? Matt. Correct. It's ultraviolet. Matter of fact, Sirius pours an enormous amount of energy into the ultraviolet. Most of its energy is in ultraviolet. And that's because the temperature for Sirius, the surface of it anyways, is 9,940 Kelvin. Quite a bit hotter than our star. It is a bigger star. Its surface is hotter, and it is the brightest star in our sky of the stars. Except for the sun, of course. The sun is the sun is a star, and it's brighter than anything, of course. But of the stars at night, Sirius is the brightest. And so it has a different mixture, so your note here, and what I want you to remember is that the combination of the three colors, violet, green, and red, are different. for Sirius because its black body spectrum is different. And its black body spectrum is different because it has a different temperature, surface temperature. Okay? So there's your chain of logic. Color combo bars, different because spectrum is different, because surface temperature is different. In this case, it's much higher. Drew.
What amount of angstroms would correspond to infrared?
700 or 7,000 or more. So here's red. This is 7,000 angstroms. Okay, and so out here, so like 8,000 angstroms. That'd be infrared. And that would be like 800 nanometers. So, questions about these two different spectra?
Not
Yes.
a question per se, but like, would it be on the test? Because it looks like the hotter it gets, the more ultraviolet it goes. Like, because for our sign, it was like what 6,000 kelvins or so, and we had more.
I cannot tell you what's going to be on the test, but you just made a very interesting statement. The hotter it goes, the what? The more ultraviolet?
It becomes short. Short is it? For ultraviolet?
The peak shifts to the left, the hotter it gets. There's something else I want you to see. The hotter it gets, the more light it puts out. And I'm going to show you a comparison of Sirius and the sun together on the same chart. Now look at this. Here we go. And so I hope you've done your sketch of Sirius. Go back to the YouTube and double check your sketch. Here's your third sketch, your third graph. This is Sirius A, the solid black line. And here's the sun, this dashed line down here. Whoa. Yeah, Sirius is putting out a lot of energy. So it's got really high radiance. The sun is kind of pokey in this scale. The sun is way down here. Okay, so not only does the peak shift to the left, the hotter you get into the ultraviolet, but the peak also goes upward because it's hotter. Okay, it's putting out more light. If you want a bright light, if you want a bright incandescent light, make it as hot as you can. If you want a weak incandescent light, make it as cool as you can. So you could do that with a dimmer. Make the incandescent light just kind of glow a little red. You get a little light, but not much. Okay, and that's what this shows you. And this, my wonderful friends, there are zillions of stars in the universe, just like ours, and there are zillions, not as many, but there's still quite a few, just like Sirius. So the stars in the universe, depending on their temperature, are going to have a black body spectrum. A lot of stars in the universe are going to be somewhere between these two. Maybe a little hotter, maybe a little cool. And actually, there's a huge number of small, cool red stars that are way below Earth's spectrum. And they'd be tucked way down in here. Very cool. And their peak color is in the infrared. Okay, and our peak color is in the green. And so we got this. This is our curve down here. This is us. We're nothing. We're nothing compared to good old Sirius A. But Sirius A doesn't have the Super Bowl or anything cool like that. Probably just a bunch of space aliens, I guess. Anyways, space aliens or not, these are examples of the continuous spectrum of stars. And I've shown you a relatively cool star, the sun, and a relatively hot star, Sirius A. Matt, do you have a question?
So this is relevant because Sirius A has about 3,000, 4,000 more degrees.
That's right. Much higher temperature. It's up there at 9,900 instead of 5,800. So it's way hotter. And that's because it's a bigger star. It's got hotter thermonuclear reactions going and stuff like that. And we'll be talking about that in a couple of weeks, why different stars are like that. Now, the reason that I'm going over this with you is, again, so that you can see the idealized spectrum in which absorption features are found, or the idealized spectrum in which from which emission features can be detected. Now, here's a smoothed out spectrum, and this is actually the sun. And let me go back to that. Here's 5890. Here's 5895. And astronomers have identified all these absorption features in the spectrum of the sun. So this top level here, that's ideally where the spectrum would be. But with absorption, you get these bullet holes here, these little things that are chiseled out of the continuous spectrum. The photons are missing. They've been absorbed by hydrogen or some other element, and therefore you have these dips, and some of them are pretty big. Now here's what some of the bullet holes look like for Sirius. Have your clicker ready because we're going to do some clicker questions. Well, let's look at the Sirius. First thing we got here is H delta and H gamma. All right, so here's H gamma, kind of a purpley blue line, and then here's H delta over here, kind of a bluish purple, and those are absorption lines. And then the idealized spectrum would be up here somewhere. But look at all these little teeny features up here. It's not just hydrogen. We've identified all these babies up here. Actually, I should say all of them except this. Look at this. There's a couple question marks here. They haven't quite figured out what these two are. We first identified helium this way. We found some dips in the spectrum of the sun that we couldn't assign it to iron, Fe. Here's Si, that's silicon. Sr, that's strontium. I believe we got titanium. Is that Ti? I think. Yeah, that's titanium over there. So we got a whole bunch of things, and you know, back in the 1800s, they figured out helium by looking at this stuff and figuring out, whoa, what is this stuff? Must be a new element. We'll call it helium because we discovered it in the sun. So those are some big bullet holes and some little bullet holes in Sirius A's spectrum. Now I have a clicker question for you, if you please. So have your clicker turned on, and let's do this question together. And keep it ready because we're on frequency AA. And go ahead and vote. In which direction would the H alpha absorption feature? Remember what H alpha is? Remember that? Well, we talked about it a week or two ago. So this is actually a review question. Trying to get you ready for the exam on Thursday. Leftward or rightward? Do you have the list? Yeah. Great. This looks perfect. Okay, so this is the lectern here.
Yeah, this is right. It's exactly
Okay.
like this. Is exactly like
Yeah, all right,
1,
good.
2, 3, 4.
All right.
And you got two seats up here, one right here. And you got some seats, isolated seats in the back.
Great.
students are
This
sitting.
looks perfect. Okay, so let's just write down lectern here. Can you tear this out and give it to me?
Yeah.
Carefully. 20 seconds to vote. Now the thing about it is when you're clicking, you don't want to operate your clicker when you're asleep. So don't get too drowsy on me. Now keep your eyeballs open. And especially on exam 1. 5, 4, 3, 2, 1, 0. All right, let's see what you... Aha! We got a mixture. This is good. I'm glad we went over this. We got some people voting for A, which is leftward, and the majority voted for leftward. And we have 40% voting for rightward, B. So let's take a look and see if we can figure out the correct direction. Okay, here's H delta, here's H gamma. Now, anybody remember the exact wavelength of H alpha? You have a... That's the H alpha line. We're not asking about the electron energy levels. We're asking about the wavelength. Anybody remember the wavelength? Yeah, what do you got? No, that's too big. That's infrared. We listed it in the notes. What do you got? 656. Okay, now here's 4,000. This is like finding somebody's house on a street. Okay, are you going up or are you going down? You're going up to the right. So therefore, H alpha, way over there, 656 or 6560 angstroms. All right? So there's your answer. Go ahead and make a note of that. And remember, the red ones are the longer wavelengths. So if you know it's a red H alpha, it's not going to be down here at the purpley end. It's going to be way at the other longer wavelength. So actually, all you have to know is that it's red. You don't even have to remember that wavelength. Remember that when you're on the exam. I might ask you a question that you think you have to have memorized some number, but if you think carefully, you'll find that there's a way to kind of put it all together and figure out the answer. All right. Now, that's all I want to talk about with spectra. I just wanted to make sure that you saw how the continuous spectrum works by temperature. And again, page 116 and 117 in your textbook is a nice little blurb about that. A couple pages, and it's pretty nicely written. Now, I want to start looking at Jupiter, and we're in chapter 8 now. We're not going to finish chapter 8 today, so we're going to do as much about Jupiter and the outer planets as we can today. And then I'll examine you guys on Thursday about it. And then next Tuesday we'll do some more Jupiter. So as much of Jupiter and stuff as we can do today, and then that'll be on the test. All right? And then we'll do some more Jupiter after the test. Okay? With a young lady with the green top. Okay, what is your name? Liz? Okay, that's it, Liz. That's the scoop. All right, so let's take a look at Jupiter. Oh, what do you call this thing? What's that called? Come on, you did some reading. A great red spot. We've been looking at it for hundreds of years. As soon as we had good enough telescopes to eyeball it, we've been tracking that thing, and it's been up there for hundreds of years. We don't know what it is. We're trying to figure it out. Lately, it's been shrinking, they say. Let's take a look at some of the spacecraft that we've sent up to observe the outer planets. The three big missions were the Voyagers, the Galileo mission, and the Cassini mission. So let's talk about Voyager 1 and 2. These are the ones that are in Star Trek, the Star Trek movies. Voyager 1 and Voyager 2, they did flyby missions. They didn't land, they didn't orbit, they just went zipping past. And this is the late 70s, early 80s. And what they did, these were some of the first spacecraft that they used the gravitational slingshot. In other words, they come and they go around the back end of a planet. The planet's going this way, and they kind of cut around behind it, and they get a slingshot. Kind of like if you're at the skating rink, whether it's roller rink or ice skating rink, and you do the whip. The guy at the very end of the whip is going to go flying because he's going to get that whiplash effect. Same thing with these. They figured out a way to do it with spacecraft. So right now, Voyager 1 is way out there, about 130. I just looked it up this afternoon before coming down here for lecture. About 134 astronomical units out, and that's considered in the near reaches of interstellar space. So it has left the solar system, we say, out there past 134 AUs. And just for comparison, the nearest star, Alpha Centauri, is about 271,000 AUs. So it's heading out there, but it's not even close to the nearest star yet. It'll be till the days of Captain Kirk and Captain Picard and all those cats' data before it gets out there and can be captured by another alien race or something like that. Here's a good website, voyager.jpl.nasa.gov/where. And it's kind of cool. They have it's continuously updating. You can tell exactly where it is. That's the website I looked at this morning or this afternoon at about 1 before I came downstairs. Get the latest specs on this baby. Voyager.jpl.nasa.gov, and you can read all about it. We have gotten a lot of good information from the Voyager spacecraft. Galileo, that's another one that was superb. Here's a picture of it. You can look at it on the NASA website. Basically from 1989 to 2003, and that one was targeting Jupiter itself. Another mission that we've sent up is the Cassini-Huygens mission, and that is still operating. We got that going in 1997, and we've been looking at data from Cassini, and it is looking at Saturn, the other giant outer planet. And we have a bunch of guys in our physics department who are planetary physicists, and in fact, our department chairman, Josh Colwell, is one of the experts and one of the science leaders for the Cassini mission. So he's an expert on all about Cassini and stuff. And here's a picture of the Cassini spacecraft. They all have these big dishes to beam their messages back to Earth. And even when it gets back here to Earth, we have to have big dishes to listen to it because it's very faint. There are many, many astronomical units out. So, and you can look at this at the Cassini website at nasa.gov. Let's take a look at some of the stuff that Voyager 1 and 2. One of the things that Voyager 1 and 2 revealed to us is just enormous detail in the outer planets. So, for instance, these beautiful swirling, dirling clouds, these littler white ovals down here, and all this stuff is weather. These are cloud formations. Way high in the atmosphere of Jupiter. It's like when we look down and see a hurricane, when you're watching the Weather Channel, and then we got those satellites up there, and they're looking down at the weather and stuff, and we see the eye of the hurricane and all that stuff. That's kind of what we're looking at here, except the fact that these things are a lot bigger than even our planet. This is way bigger. Earth would fit multiple times into this image alone. Neptune. And here's the thing that we didn't know about Neptune. We found it when the Voyagers went by. This is called the Great Dark Spot of Neptune, or the Blue Spot. Here are different names for it. Neptune has this, and it looks like a hole in the sky. Now, we don't know what it was. I remember when I went to grad school in 1990, everybody was talking about this. But a few years later, when the Hubble Space Telescope was up and they turned their eyes toward Neptune, this great dark spot had vanished. It was gone. So this is we think it's some kind of a storm in the atmosphere of Neptune, but much shorter duration than the great red spot on Jupiter. So the Jupiter great red spot, big huge storm, about the same proportion as this one. I mean, if you look at both of them as circles, this is taking up about as much of Neptune as the great red spot takes up of the circle of Jupiter. But the great red spot on Jupiter is very long-lived. Very long-lived. It's been going for hundreds of years. We don't know if it's ever going to stop in our lifetime, but we're going to keep looking at it. But Neptune, yep, this one, it's out of here. And we might see another one pop up. Maybe we were just lucky that this one had lasted for thousands of years, and we just happened to catch the last couple of years of it. We don't know. But, you know, we're going to keep looking. Enceladus. Oh, baby. Now, this one is about the size of Florida. So think of this, you know, it looks like a moon. You know, you can see these ridges on it from deformations in the surface. It's about the size of Florida, from Miami all the way down to Jackson, or from Miami all the way up to Jacksonville, about the diameter of Enceladus. And we've seen close-ups of all kinds of other moons. Here's one of the moons of the moon Titan. And this blue stuff here is an atmosphere. It is a moon that has enough gravity to retain an atmosphere. It's very interesting. Jupiter has rings. You didn't know that. Until we got up there and sent some spacecraft up there to find them. To look for everything we could find, and we found rings for Jupiter. So they're not nearly as big as Saturn's rings. But yeah, they're up there. Let's take a look at the stuff that we observed from Galileo. Galileo was meant to orbit Jupiter, and it sent a probe down into the atmosphere of Jupiter. That is the aurora borealis on Jupiter. If you've ever been up north, there's the aurora borealis, the northern lights. They are magnificent. Anybody here ever seen the northern lights? One. Raise your hand high. I want to see. 3, 4, 5. The northern lights. One time I was up in Montana. I've seen them up in northern Quebec, and I've seen them in Montana up in the mountains. And I was visiting a friend, and I parked my truck at the end of this dirt road, and then I walked into this cabin where my friend lived. And then when I left later, it was dark, and I was walking down this road through this big clearing on the side of a mountain. And so you could see the entire sky, well, except for the part right by where the mountain was. You know, so you got this big mountain up behind you, but then away from the mountain, you can see everything. You're up at an altitude, and it was dark. And out in Montana, on a dark night, you could see everything. I mean, so I'm out there, I'm walking, I'm just thinking, or, you know, or maybe trying to digest my dinner or whatever it was. And I'm walking down this road back to where my truck was parked because I didn't want to tear out the transmission trying to get all the way into this friend's house. So I parked out there about a quarter mile from their house, and I looked up at the sky, and oh my goodness. From the east to the west, from the north to the south, it looked like the sky was burning. Kind of orangey red and purples and greens, and it was just all changing and whirling and swirling. And it was, at first I thought the Russians had attacked and that we were in the process of being nuked. And I thought, oh my God, this is it. But it was, then I thought, oh no, this is the Northern Lights. So I went from having a heart attack to having a joyful experience. And it was magnificent. The entire sky. Now, most of the time you don't get that. Most of the time it's off to the north. If you're here in the States, it's off to the north and you can just barely see it on the horizon and they flicker and stuff. But if you go up to Alaska or something, or if you're in Montana up in the mountains and it's a good night, you have a really intense aurora, you can see the whole sky lit up. It's just fantastic. And that's what we see here. Now, most of the time on Earth, the aurora borealis looks like that. I mean, if you see it from space, and we have satellites up in space that are looking down and observing, all the conditions all over the planet. And usually the aurora borealis does form a ring on Earth, and the same thing here. So this is the 70 degrees north latitude. Here's on Jupiter. Here's 60-degree north latitude. So the Arctic Circle for Earth is about 66 and change north latitude. And so you can see that this aurora borealis goes a little bit further south than it would on Earth most of the time. This is a pretty big planet, and that's a pretty big aurora borealis. If you were down there flying around in a spacecraft in the atmosphere of Jupiter and you were looking up at this thing, it would be awesome. It just would take your breath away. And you'd see all kinds of color. And it would look different from Earth because the atmosphere of Jupiter is different. Question? Intense magnetic field of Jupiter and the solar wind. The solar wind burns off the surface of the sun. It's mainly electrons, protons, and the nuclei of helium atoms. So the nucleus of a helium atom is 2 protons and 2 neutrons usually. And in the way the sun works, those things are easily burned off and streamed off the surface of the sun in all directions, and they form space weather. And when those particles in the solar wind interact with the magnetic field of the Earth, they start curving around and spiraling around, and they generate electromagnetic fields that we sometimes see as visible light. And they generate radio interference. The aurora or the solar wind can actually, if it's really intense, can knock out entire power systems, and has done so. Up in Canada and Minnesota, places like that. And, the northern latitudes are more susceptible to it. But if there's ever a big, solar event on the surface of the sun, it'll knock out everything on the entire planet. I mean, we hope it never happens in our lifetime, but if there's a big, what they call coronal mass ejection, CME, and if it's not, a lot of times it can be ejected in any direction. It can be ejected away from the Earth. It can be ejected toward the North Star or, the other direction. But if it's ejected toward Earth and if it hits the Earth, it can knock out the power grid worldwide. We'll be back in the 17th century. Except for the military, they probably survive it. They've hardened everything. So the Air Force will keep flying, but other than that, the rest of us will be toast. Here's a lightning storm in the atmosphere. Look at that lightning. These intricate details in the surface. We actually have guys that are trying to figure out what is happening with this. And it's kind of interesting. It's very difficult to model. Any kind of fluid mechanics is very tough to model, but from the Cassini and especially Galileo, we've been able to get a lot of good data on that. Now, I want to turn to the basic specs for the outer planets, and let's do some talking on this topic. This is a fairly important figure in Chapter 8, Figure 8.1, because it shows the accurate sizes of Jupiter, Saturn, Uranus, and Neptune compared to each other. All right? Now, they're so far away, they'll never actually look this way. But if you could stand in one place and take a photo of each one and then kind of Photoshop them next to each other, they'd look about like this. Okay? So, the Jupiter and Saturn are the big ones. Uranus and Neptune are smaller. Here are the actual diameters. Don't jot them down, but just jot down figure 8.1. And down here in the little writing here in figure 8.1 are the diameters, the mass, and so forth, the basic specs of those four outer planets. And if you notice, Uranus and Neptune have a diameter approximately the same size, about 50,000 kilometers. Jupiter and Saturn, they're up there above 100 and change, 100,000 and change for their diameters. So that's good. If you scale them down to this scale, Jupiter and Saturn about the size of a basketball, then Uranus and Neptune are going to be about the size of a baseball. So that's a good ballpark scale for Jupiter, for the outer planets. Basketball for the big ones, baseball for the two little ones. It's pretty close. Now, I'm going to ask you a clicker question. So have your clicker. And it's using the same scale. Okay, if Jupiter is the same, if Jupiter were scaled down to the size of a basketball, okay, Uranus and Neptune would be a baseball. Now let's think about some of the other planets. What would the Earth be? Go ahead and make your best guess. Mosquito, nickel, softball, or an atom? Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Yeah, this is good. We got a good distribution, a lot of opinions here. Let's see, a lot of you voted for B. But a bunch of you voted for A, C, and D. And the answer to this one is B. And so if you think about a nickel versus a baseball versus a basketball, that's roughly the proportion of Earth. So Earth is like shrimpy compared to this stuff. This is what Earth would be. You know, Earth and a nickel. Jupiter basketball. All right, let's go the other way. In the Jupiter basketball scale, how big might the sun be? A chair, a regular sized door, football stadium like Bright House, a chute. Fifteen seconds. 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Yeah, it's good. Whoa. You guys are changing your votes. Here's the mixture, and let's see. Some of you voted for A, some for B. Bright House. A lot of you guys voted for Bright House. The majority did. And if you changed your vote to see? You are wrong. It's not Bright House, it's a regular sized door. So, in other words, one of those doors back there. So, if a basketball is laying on the floor, then the sun would be about a sphere about as tall as that door. And a nickel would be the earth. So, that's about right. Now, next question. Jupiter is pretty large, right? How big is the Great Red Spot? If you did your reading, and if you looked at the diagrams in the textbook, you'll know the answer to this. So this is actually a homework detector. 15 seconds. Five, 4, 3, 2, 1, 0. Bing. Close. Check. Uh-oh. We got a bunch of geniuses in here because, is that incredible or what? So check this out, right? This red spot here, it's not a hurricane. They think it's a high pressure storm, not a low pressure storm. So it's not exactly the same as a hurricane, but it's a storm. And inside that storm, you could fit 2 planet Earths. You know, one here on the left side, one here on the right side. What? But that's how big Jupiter is. Oh, side note. Aurora Borealis on Jupiter. Jupiter, because the magnetic field of Jupiter, Jupiter has the biggest magnetic field in the solar system. And that is one of the reasons it has these big aurora borealises. Way more powerful than Earth's. Mars is pretty weak. Earth's got a decent one, and it's not that strong. But Jupiter, whoa, it's ginormous. And everything about Jupiter is ginormous if you're a planet. But of course, if you're the sun, Jupiter's not even a spit in the bucket. It's nice and everything, but the sun is mighty. The sun is mightier than Jupiter. All right. Now, I don't want to talk any more about Jupiter until next Tuesday, but what I do want to talk to you about is getting ready for exam 1. All right. Now, we've been lecturing, as I mentioned last time, chapter 3, 4, 5, 6, 7, and 8. We're in 8 now, but we haven't covered everything in each chapter, so don't be the slave of the textbook. Let your lecture notes be your guide. That's your main study guide. If I talked about it in lecture, go and find it in the textbook. Also, secondary to lecture homework, in other words, masteringastronomy.com. In other words, the mini assignment for tonight in the extra readings, yeah. Also, iClicker questions, which technically they're part of lecture. So if I ask you questions using the iClicker, it means I think it's important and it's worth quizzing you about in class, maybe even in the exam as well. All right? Now, your lecture notes, so don't ask me for a study guide ever, because study guides are for high school. All right. That's what my son is a junior. His teachers give him study guides. Okay. I don't do that. No. We're mature, supposedly. So no study guides here. Your lecture notes are your study guide. Third level importance, reading in the textbook that supports lecture. I already mentioned that. Okay, be here and ready at 1:30 p.m., if not sooner, and I'll be here ready. You're not ready to be dismissed. Don't get up yet. Bring yourself a raspberry colored UCF Scantron with the Pegasus logo, a pencil, and a good eraser. You know, we had a guy in the morning class. We gave midterms last Thursday for my physical science class in the morning, and they got their printouts back. And one guy had a bunch of errors because he didn't erase well. All right, so bring a good eraser. One of these pink jobs from second grade is best. Calculator is permitted, but no cell phone is permitted. You may not use your cell phone for any reason. But if you need a calculator, if you have a calculator, bring it. Bring your iClicker too. And we're going to have a bunch of questions. So listen up. Here's how it's going to be. My physical science morning class, we had a midterm exam, 45 Scantron questions, 5 clicker questions. Actually, 3 clicker questions worth 5 points. Okay? And I may do something similar to you guys with that. Also, the formulas. The first 4 or 5 questions on the test will be matching. I'll give you, like 3 formulas and then 5 definitions or concepts, and you'll match them up. And then maybe another 2 or 3 formulas and another 4 or 5 concepts, and you'll match them up. And that way you'll have every formula that you're not going to need a whole lot of formulas. Like maybe we did a calculation of delta a couple weeks ago, delta 18 oxygen. I may ask you to do something like that. And if I do, it'll be in the matching part of the first 4 or 5 questions, 6 or 7 questions. Okay? We don't have a huge lot of formulas. Then multiple choice, maybe some true false, and maybe a calculation, but the actual calculation will be on the iClicker. Okay, so you'll be typing in a number. Everything and I'll have instructions on the test on how to use the iClicker during the test. Instead of working off the computer screen, you'll be working off the test paper. Try to study with at least one other person, human being, if possible. And on the exam, I want you to read every question very carefully. All right, as if it was a Terminator telling you. This is very carefully. Questions about the exam before we dismiss? Okay, I have office hours tomorrow, 9 o'clock to 10:30. Mini assignment and web courses, review for exam 1. I'll see you on Thursday. You're dismissed. 2:37.
Should I announce well, you already put it on there. You already